Welcome to Train Signal. You are watching Advanced Storage Management. So we're going to dive right in. We're going to start by talking about some storage functions. And what you'll find is that, the blueprint for the exam covers a wide gamut of things. So I want to make sure that you understand all of that. Some of this may be reviewed. You may understand RAID levels very well and the differences and the pros and the cons and all that, but you may not. And I think it's good review, especially since the blueprint does talk about, choosing the right underlying storage for the right workloads and things like that. So, with that bit of a disclaimer, we're going to start with RAID levels, then move to some of the other more advanced functions of vSphere. We won't hit all the RAID levels. I'm going to talk about 0, 1, 5, 6, 1 and 0, and 0 plus 1. Those are the main ones that you see used today. The other ones like 3 and 4 and stuff like that aren't nearly as common, so I don't think they're really worth discussing, but we'll go over the majors. So RAID is redundant array of independent disks. Some people used to say inexpensive disks, but I think independent is a little more common these days. But the idea is you combine multiple disks for performance and or redundancy reasons. And the key is finding the right balance, because as you'll see, some RAID levels will give you better read performance, some will give you better write performance, some are more resilient than others, and there's just different use cases, so you have to pick the one that's right for you. The sad thing is, well, not sad, I guess, the good thing is that with the advent of flash storage, this is becoming simpler, because it's just really, really fast, and we can just do some simple things like, simple RAID 5 or something, and we don't have to do as many tricks to get the I/O where we want it. But we're still living in a world with spinning disks, so that's what we're going to mainly focus on here. And really, one thing that I see in virtualization, and I probably should have put this at the top, but it's traditional silos start to blur within IT when we start to virtualize workloads. I do a lot with networking. That's what I often speak on at VMworld. That's what the courses I've done as well. And we see VMware admins have to kind of move into the network space and understand that better. And I see VMware admins have to understand the underlying storage. Now, they don't have to know it as well as a guy who's been doing it all their life, but you do need to understand it at a decent level so that if you have, performance problems with a VM or you need to troubleshoot something, that you'll be able to understand what's going on. So that kind of blends in with a lot of what we're going to talk about. So we're going to jump into the first RAID level, and it is RAID 0 or disk striping. As you see, it basically takes data and writes one disk, the other, back and forth, back and forth. Now this is 2 disks. You can go up above. You could have 10 disk stripes if you wanted to. You could have, 16 disk stripes if your array supports it. The thing is, it's going to take a write when you write a block of data and stripe it across those disks. When you read, it's going to read across. So you get very fast performance, very quick, very fast writes, very fast reads, and you just have to make sure that that's what you want, I guess. But the idea is you have to make sure and understand that there's zero reliability. And that's one easy way to remember what RAID 0 does. There's no mirroring, secondary data. There's no parity, anything like that. You just write the data, read the data one-to-one. If I should lose disk 1 here, I lose half my data. If I have 10 disks in a stripe and I lose one, I lose 10% of my data, and I have to, rebuild the stripe set and restore the data from a backup. So again, better performance, but no reliability. Minimum of 2 disks, obviously. If it's only 1 disk, you're not striping, up to however many your storage systems support. But remember, additional disks increase your risk of failure. So your mean time between failure, if you have 10 disks, it on average is going to be like a tenth of that. So as you add disks, your likelihood of a failure goes up. So if you do use RAID 0 for some reason, you think, I need something really fast, I don't care if it dies, I'll just restore it. Keep in mind, the larger you go, the more often you're going to be doing that restore process. Data is striped across all available disks. We just talked about this. Increases both read and write performance. And capacity is the amount across all disks. So if those are 1 terabyte drives right there, I have 2 terabyte usable. If I had 10, I'd have 10 terabyte usable. There's no loss of capacity for parity or for mirrored data. 1 disk fails, you lose all of it. Again, even if you had 10 disks in a set, all it takes is 1 failure. So now here's RAID 1, which is like, it's disk mirroring. So as I write data, it's 1-to-1. So write the blocks here, it gets copied to there, back and forth, back and forth. So when I write things, it really only writes them to one disk. The disk controller will write them to both, but I'm not going to get additional throughput. When I read them, I can read off both sets and get additional throughput. You made up a pair of disks in a mirror set, only 2. So I can't really mirror 3, 4, 5. If I do that, we're going to start talking about RAID 10 or 0, 1, and we'll talk about those in a minute. So normally RAID 1 is just a mirror of 2. All writes are sent to both disks at once, provides redundancy, does not increase the write speed. Reads are serviced from either disk, speeds up reads as both disks can service the requests. Failure of a single disk does not cause loss of data. You basically pull that drive out, slap another one in, and have it rebuild the set. Some arrays will do it automatically, some you have to say go do that, but in the end it's going to copy everything from disk 1 back to disk 2. You only get 1 drive's worth of capacity since data is duplicated. Fairly obvious, but if those are 1 terabyte drives, I'm only going to have 1 terabyte usable because the other one is going to be a set of mirrored data. Now let's talk about RAID 5, striping with parity. RAID 5 sets are made up of 3 or more disks, and they provide what we call N+1 redundancy by utilizing a parity stripe. Parity information is data that can be used to rebuild the set should a single drive fail. It's built using binary XOR operations normally. But the idea is I write data across. Let's say I have 3 disks. 2 of them will have data. I'll write to disk 1, to disk 2, and then calculate a parity. And then I keep doing that so that if I should fail disk 2, I can take the information on disk 1 and the parity information on the third, or the remaining disk, and recalculate or rebuild what was on disk 2. Reads and writes are striped across all disks. Writes take what we call a write penalty or a parity penalty when they're written because you have to calculate the parity and we have to write it to disk and we're not actually writing data. So there is a bit of performance hit. We'll talk about that in a minute. There is no penalty on a read because I don't read the parity data. But if you have 5 disks in a RAID 5 set, when I do a read, I'm going to stripe the reads across 4 of the 5 each time because one of those is going to have parity. So you don't quite get all of it, but you get most of it. Capacity is the sum of all disks minus 1. So if I had 4 by 1 terabyte, I would get 3 terabyte usable because 1 terabyte is for parity. Now, I'll show you this in a diagram, but to kind of hit on something, you don't dedicate one drive to parity. That's actually called RAID 3. Parity is striped across the disk as you go. So the parity stripe, a stripe on a disk is settable in size. It may, if I might write a meg of data, 1 megabyte, it may put 64 kilobyte or 128 kilobyte on each disk as a stripe as it goes across. That's usually settable by the array or the controller. But what happens is that on the first pass it may write data on 1, 2, 3, parity on 4. Then the next one it'll write data on 1, 2, 4, parity on 3. It's spreading that parity across to help with performance. And here it is on a diagram, better than what I just went through. Basically disks 1, 2, and 3. It's writing a data from A to F, A, B parity, C parity D, and then parity E, F. It's spreading that across. And so if I lose disk 1 here, I can rebuild this. So first of all, if I lose disk 1, the volume doesn't go down. If there's VM sitting on this volume, they don't die, they don't crash, they don't blue screen. Because on the fly, your controller or your array will start to read data and say, okay, we need to read A. We don't have A. Well, we do have B, and we do have the first parity stripe. We can figure out what A was from that. So A, B, we're good. Now we need C. We don't have C. Well, we got parity stripe 2 and D. We can figure out what C was. All right. Now we need E and F. Well, I already have E and F. I don't have to calculate that. Point is, your reads are going to take a performance hit because now I'm doing calculations on reads. And I'm going to do calculations on writes. So your performance is going to suffer, but you're not going down. Pull that disk out, bad one out, put a good one in, tell it to rebuild, and in the background it'll start rebuilding this data based on the remaining surviving parity. Again, you'll take a performance hit as those calculations run, but nothing goes down. So RAID 5 good, fast on reads, does take a penalty on write, does have a good usable capacity calculation because we're only losing 1 disk worth of capacity to parity. We used to do a lot of, well, I guess we still do a lot of RAID 5 sets. The majority of the VM workloads we do with customers are on RAID 5. Normally they are what we call 4+1 RAID sets, which means they're 5 disks. We say 4+1 because it's 4 usable plus parity. Used to do 8+1s, which were 9 disks. So there's different ways to do that, but very, very common. Then there's RAID 6. RAID 6 sets are made of 4 or more disks. The idea here is it uses a second parity stripe, so we can fail 2 disks. Why do we want to fail 2 disks? Well, more's better, obviously, but more importantly, disks are getting large. I'm sitting here looking at one of my NAS boxes. I use Synology NAS in my lab, and one of them's got 3 terabyte drives in it. Actually, there's another one I use that has some media on it, movies I've ripped, things like that for my son, that is 5 2 terabyte drives in a RAID 5 set. I failed one of those the other day. So I pulled it out, got another drive, slapped it in there, said rebuild, and it took something like, how long did it take? I think it was 18 hours. That may be wrong. It was something around that time of about 18 to 24 hours. Now, what happens if I had failed a second drive within that 18 to 24 hour window? I'd have lost all the data. So we have what's called a rebuild time. And then you have in RAID 5 what we call dual disk failure. You're rebuilding, and man, you roll the dice and you lost, and you just failed a second drive. Now you're pulling tapes or something to do a restore. So now we have RAID 6. Very common as we go up in drive sizes. So RAID 6 does N+2, so you can fail 2 drives. Parity is basically the same. There are some variations, so that really probably shouldn't say built using binary XOR. It would say often built using binary XOR, because some people have tried to develop better methods for doing parity on RAID 6 to kind of reduce the write penalty. But in the end, just remember it's 2 parity stripes. Reads and writes striped across all disks. Writes take a penalty more than RAID 5 due to parity calculation. Again, there's no penalty on read. Capacity is a sum -2. So if I have 4 by 1 terabyte, it gives me 2 usable with 2 for parity. If I had my NAS down there doing RAID 6, I have 5 drives by 2 terabyte. So that would have taken me down to 6 terabyte usable, 3 usable, 2 of the drives not. Whereas with RAID 5, I had 8 terabytes usable instead. So that's a big reason I did it. The other one was performance, but hopefully I won't have a double disk failure. But just keep in mind you do lose 2. It's common to see some larger RAID 6 sets. I mean, it's not uncommon for us to do what we call, again, a 12+2, which is a 14 disk RAID 6 set. And we can fail 2 disks. So if we fail one and we're doing a rebuild, we can fail a second one and continue to run. Now, if we fail a third one, it's a bad day because you got to do a restore, but hopefully you'll be rebuilt by then. So here's the diagram. As you can see, pretty simple. A, B, 2 parity stripes. C, 2 parity stripes. D, parity stripes E and F. So if we fail a disk, we can recalc like the missing E here based on the parity stripe. If we fail 2 missing disks, we can recalculate a lot of this again off the parity stripes. So it's an interesting way to go. We're seeing it used more and more again as the 2 terabyte, 3 terabyte, and 4 terabyte drives start to show up. So now let's move on to RAID 0+1. The idea here is higher performance. And since nothing's free in life, you'll see that we give up capacity for the performance, but sometimes that's fine. Sometimes budget allows us to do things like that. So the idea here is it combines both RAID 0, remember that is striping without any parity or protection, and RAID 1, which is mirroring, into what we call mirrored stripes. So it stripes data across 2 or more disks and then mirrors them to an equal size set. You need a minimum of 4 disks, or as we'll say, that's 2 stripes. Stripe of 2 mirrored to a stripe of another 2. Now, some implementations I've seen this, they're usually kind of these odd edge corner case, controllers and things like that. Will actually let you say like stripe 2 1 terabyte drives and then mirror it to a 2 terabyte drive. But to me, that's a terrible idea because of performance implications. And really, storage is getting so cheap these days that I just would never do that. But it's out there. I just want to make you aware of it. But I would do it kind of the traditional way, where you have equal size mirrors across the board. The neat thing is you can fail 1 or more drives in a stripe, but you can't fail a drive in both stripes. And this will probably make a little more sense here in a minute when we get to the diagram. It does offer very high performance. So we've talked about write penalties and things like that. There is a write penalty even though we're not doing RAID. but it has to do with how you write down, and you have to write multiple copies of the data at one time. But it's still very high performance, and we'll run those numbers here in a minute. But it's at the cost of high overhead. With these, since we are mirroring, obviously, we're going to have two full copies of data, so we only get 50% capacity. So that's the downside to 0 plus 1. And here's a nice little diagram. So what you can see, grab my pointer, is we have a RAID 0 set. So we stripe across these two disks. Then we mirror these to another RAID set. Stripe, 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 stripe. Very high performance, because when we write, we're writing by both stripes. When we read, we're pulling data off all these disks. So you can imagine this where we may have, 10 disks over here, mirrored to 10 disks over here. You can get very high performance like that. So you can make these much larger, much better, and this is how we can really give applications very high IOPS off of a single set of spindles. Now, for failure, what you can do is take a look. So again, you have mirrored copies of data. So I can fail this disk, and then I could, actually fail this disk, whatever. But you have to be careful, because we fail this and we fail this, like both disks holding A1, we obviously don't have another copy of A1. We'd lose data, have to recreate and go to tape or something and do a restore. Depending on your implementation, you may get lucky. You could fail, say, this disk with A1 here and this disk with A2 here, and still kind of pull data from each. Just depends on your implementation. But the idea here is 50% high performance, but it's kind of, I can't tell you how many disks you can fail, because it just kind of depends. You just got to remember you can't lose all copies of a data set. Then kind of a flip side is what we call RAID 10, or 1 plus 0. So it combines both RAID 1, mirroring, and 0, remember striping without parity, into striped mirrors. So at first you're like, wasn't that what you just showed me? And the answer to that is no. You'll see that in a second. The idea here is it's multiple mirror sets of drives, then the data is striped across the mirror. So before we had stripe sets and we mirrored those, now we have mirrors that we do with stripe sets. Again, a minimum of 4 disks or 2 stripes. And you can fail 1 drive in every mirror set. 2 will take out the mirror and cause loss of data, kind of a game of odds. So let's take a look. Again, high performance, 50% overhead, and let's take a look. So let this draw. And so what we've got here is a mirrored set of disks, a mirrored set of disks. When we write data, we write them to this mirror, we write data to this mirror, and then we stripe across them. The nice thing is we can keep extending these mirror sets out and stripe across a bunch of them. And then if we have a disk failure, we could fail one here, we could fail one here, we could fail one way down the line. Again, you just got to make sure you don't fail 2 of the same kind. Nice thing here is if you fail this disk and we replace it, it only has to rebuild this one mirror set, not a big large stripe of data or anything like that. So it's very quick. For these reasons, it's pretty common to see this. Again, it's just kind of depending on your implementations and how you want to do it, but it's a way to get very high performance. Matching your workload I/O requirements to your backend storage is key. This is something we do a lot when we work with customers. We go pull a lot of data off their applications and figure out what kind of backend storage they need. Is it, SATA disk, 7200 RPM? Is it 10K, 15K SAS? Is it solid state? Then what RAID they want? Is it, what's their budget? How do we fit that in? Do we do RAID 5? Do we do RAID 6? Do they need high performance and are, have the budget for 10 or 0 plus 1? What do they need to do? And so you have to look at your I/O requirements and then match them up. Honestly, sometimes it's more of an art than a science. There's a lot of great tools to pull data, but we've still pulled data, matched everything up, thought, man, this is great, put it in, and still had issues or things changed. So don't be surprised if you do this and then you have to make a change. But all the work you do ahead of time to kind of size up your workloads does pay off in the end every time. This is something you probably won't hit. I don't think they're going to have you do workload calculations within the exam. At least that's not mentioned in the blueprint. But it's something that we run into a lot, and it's really the #1 cause of performance issues in a virtual environment. It's not CPU, it's not memory constraint, it's very often storage. So common tools that we use, perfmon for Windows. You can pull great IOP information and write information off perfmon. IOstat for Linux. Some vendor-specific scripts and tools. I've got things that we're a big EMC partner. I've got EMC tools that will help me size Exchange or SQL or a lot of other things and figure out what kind of back-end disks we need. vScuzzy for virtual workloads, ESXtop. We're going to talk about those two in another lesson so that you understand those. But there's a lot of tools out there to gather this data. First, you want to define your I/O profile. Is it read heavy, write heavy? What kind of I/O? Most common applications, I'll say, are 70-80% read, 20 to 30% write. But you may have a database that's doing inventory or taking information in that's 80% write and 20% read, and you put that guy on RAID 5 or RAID 6, and you're going to have to add a lot of disks. You're going to have to add a lot of capacity when you could have done it easier and better with RAID 10 or 0+1. So look at those. Don't just go by industry standards. All right, I'm guilty of this as anybody, right? I just said it. I just said, it's commonly to see 70-80% read, but it is. But don't assume. Start with that information and say, well, I suspect that this is going to be something in the norm. And then if it's not, figure out why. But don't just assume it will be, or you're going to end up in trouble one day. Choose your RAID type and storage to match. So I just kind of went over the high levels RAIDs, the common that we see. But you can understand, and we'll talk about the write penalties and things in a minute. But you can see where you'd start to have issues if you were write heavy on a RAID 5 or 6 volume, or you were read heavy and then you did RAID 10 with a bunch of disks and you wonder why you chewed through your budget. So just kind of start matching those up. And don't forget about other factors. Well, that's the miscellaneous thing. But, growth is important, budget is important, sizing is important, capabilities of your RAID or your SCSI controllers are important. All that factors in. So there's no simple cut and dry rules for how we do this, but it does give you an idea of what you need to look at as you build this out. It's common to see people say, hey, we do everything on RAID 5, and it works great until they have a big write-intensive database, and then it just goes terrible. So keep that in mind as you start setting so-called standards as well. So now let's talk a little bit about understanding real-world performance. And what I mean by that is, how do you calculate, how many spindles and disks and things like that, what kind of RAID type you need given a certain set of workload information. So different RAID types have different what we call I/O penalties. And we kind of touched on this throughout. It has to do with how much of a hit you take when you write data. Your RAIDs, your 5 and your 6s, because they have to write data with parity, have a much higher write penalty than, say, RAID 10 or 0+1. So here's some kind of rules for normal disks. These are back of the envelope calculations. I don't think you'll need to know this for the exam. I mean, I would be surprised. I'm actually very surprised given the blueprint. I don't think they're going to need you to calculate this. And honestly, these are not hard and fast numbers. These are numbers that I use commonly from EMC and others, but they do vary slightly. And the idea is these are the number of IOPS you can expect out of a single spindle. Normally, these are kind of worst case scenario. They're based on rotational speed of the disk, meaning if a disk head is sitting over one piece of information and the next one just went under it, as the disk spins, it has to wait a full rotation before it can come back again. And that's why as the disks get faster here, 7200 RPM, 10K, 15K, you see the numbers go up because the disk spins faster. So I kind of take these as worst case. Now that doesn't mean, as you'll see in a minute, that we can take 10 7200 RPM drives and get 900 IOPS. It means that that disk can deliver 900 IOPS, but depending on the RAID type and the configuration, your actual IOPS will be different, usually less. Though, again, I say usually less, but really, since this is worst case scenario, if you had like a sequential read, like, 10 IOs in a row on the disk, you're going to get much higher than 90 IOPS on a 7200. But you can't really estimate that, so we use these kind of worst case numbers. So, 7200, 90 IOPS, 10K, 130 IOPS, 15K, 180, and Flash is kind of this mystery. Flash continues to evolve. I usually say 2K to 4K. It depends on several things. Many flash drives do more higher IOPS reading than they do writing. It depends on, MLC, SLC, and some other stuff. It also depends on the implementation, and things are getting better. Right now, I say 2K to 4K. Just know they're really fast. How about that? But that's probably about close enough. And here's a RAID type and your penalty. So 1 has a penalty of 2, 5 has a penalty of 4, 6 has a penalty of 6, and 10 has a penalty of 2. So you can see that it's, definitely RAID 10, as you'll see in a minute when we work the numbers, gives you a big advantage over 5 and 6. Some things are kind of making these a little bit simpler. Front-end caching using flash drives and things like that can soak up, as we say, a lot of writes before they go back and get flushed to spindles, so you don't notice the write penalties as much. But if you start doing a heavy write workload, and let's say, I got 600 gig of SSD on a storage array that's acting as read-write cache on the front from all hosts, and then when it can, it flushes things to the back-end spindles. If you're writing so fast that you're overrunning the back-end spindles, then eventually you start writing through and you run into these problems. So don't just assume things like they're going to fix all your problems. You have to understand your workloads. And they're nice, but, they don't solve everything. So workload is often characterized by IOPS along with read and write percentage. So I hit on this a minute ago. Some other factors apply, such as I/O size. What I mean by I/O size is when an application does a write, a single write IOP, how big is it? Is it 4K, 8K, 32K, 128K, which is a real big write? That matters because you want to kind of match your stripe sizing on your back-end systems to match those. Now, if you're like most people in a VM environment, you got all different apps running as VMs on different data stores, so it can be hard to do that, so you may just go with whatever your array vendor recommends. But it's important to understand those things and understand what your profile looks like. And how many IOPS can you get with a set of disks? I'm not going to do the numbers, but here's how you do the numbers. Again, I don't expect on the exam to have you do math. They don't give you a calculator for this exam. They just give you a little dry erase marker, so I don't expect you to have to do too much math. But for your information, if you want to know the total raw IOPS, it's disk IOPS times number of disks. Well, that's pretty simple. Functional is raw IOPS times write percentage divided by read penalty plus raw IOPS times read percentage. You can run those numbers and take a look, but that'll give it to you based on which RAID type that you use. How many disks are needed to achieve a required IOPS amount? I run into people all the time and say, well, how busy is that database? It's about 4,000 IOPS. All right, well, let's see how many disks we need. So disk required equals, you can see it here, read IOPS plus write IOPS times penalty divided by disk IOPS. Simple formula, but, something to use. An example, you have 10, 15,000 RPM SAS drives. I don't care about capacity. Capacity does not denote performance, at least from an IOP standpoint. It actually would for a throughput. Higher density disks often have faster sequential read and write, but I live in a world where sequential read and write is not key. It's usually the IOPS. So you have 10 of these, 180 IOPS per disk, back of the envelope number, 180 times 10, 1,800 raw IOPS. Common workload, 80% read, 20% write. I'll also flip that for this example. So you take a look at it. So remember, we started with 1,800 IOPS. RAID 5, 80% read is 1,530. But flip that and you see we cut it in half. Actually, it's worse than that. And as you go down, RAID 6, RAID 10, you see why RAID 10 becomes popular, because it doesn't have nearly the write penalty that the others do. So, it's just something to keep in mind. And now as I say that, I think I said earlier that there was no write penalty, but there is a small write penalty, obviously. But as you see here, and also back to my write numbers, but it's not nearly as bad as 5 or 6. So you want to make sure that you look at these. If you're a heavy write environment, 5 or 6 is probably not the way you want to go. Some best practices, recommendations: dedicate disks whenever possible. Don't carve up disks in an array where they are used for both a data store and other workloads. It makes your job really tough, because you're going to have somebody complain about VM performance. You're going to look at your information, and it's going to tell you your latency is high. And you're going to look at your VMs and go, that's weird. No, the VMs are really hitting the disk. Why is latency so high? And you start digging, you start looking, and then you're going to go to the array, and you're going to start pulling information, and then you're going to pull up like a health chart on the array or a heat map for those disks, and they're going to be bright red flashing at you. And then you're going to remember, oh, that's right, I gave half of those to the dev team because they needed some capacity a couple weeks ago, and they're hammering those disks. So I don't write your budget, But my very big recommendation, as someone who does this a lot, is don't mix disks. Dedicate disks whenever possible. When you update your array software, confirm your settings. We'll talk about multipathing and all that stuff in a later lesson, but it's important to understand here. EMC arrays, something I deal with often. VNX is their kind of what we'd call their mid-market array. Their multipathing suggested selection has changed depending on the version of what's called the operating environment, OE, that is running on it. So when you update the OE, check the release notes and make sure you don't need to flip it from, say, fixed to most recently used or round robin, because that's going to be important. You may have some issues if you don't do that. So anytime you update software, confirm your settings. Try not to oversubscribe storage links. So we haven't really hit on NFS and iSCSI. That's coming later, but don't oversubscribe them too much. And I still run into people who think adding a VLAN somehow magically makes throughput or bandwidth, and it's not the case. If I have a 1 gig connection and I have 1 VLAN on it, I get 1 gig. If I have 100 VLANs running over it, I have 1 gig. So just be careful. Don't oversubscribe your storage connections very much or at all, because you don't want to start dropping frames and you don't want to start having problems, because it makes performance exponentially worse anytime that starts to happen. New array offers flash and other tiering. So storage advancing quickly. All the stuff I talked about is going the way of the dinosaur. We're moving to storage arrays with flash on the front end for cache. I do arrays all the time with hundreds of gigs or terabytes of front end solid state disk for caching that soaks up a lot of these write and write penalties on the RAID 5 and RAID 6 and makes my life easier, to be honest with you. We're also moving to the world of all flash arrays, and we're moving on beyond RAID into other forms of algorithmic parity calculations. So it's important to remember all this stuff, because we're all going to be dealing with it for years to come, but it's getting better. We also deal with arrays with automatic tiering. Again, I deal EMC, so I talk EMC. But we can have arrays with 7200 RPM SATA, 15K SAS, and solid state. And as data gets hot, it gets moved to solid state. As it cools down, it goes to SAS or to SATA, all automatically within the array. It makes performance tuning simple, but it can also cause problems with things like storage DRS. We'll talk about that when we get to that lesson. But it's something to keep in mind that this is evolving and it's changing for the better for sure. Sometimes you guess, analyze, and then correct. I said it's more of an art than a science. It's more of an art than a science at times. Multiple VMs in a data store can make it tough. One example I like to give is I have 3 workloads that do a lot of sequential read and a lot of sequential write. Think of file servers, something like that, or something holding imaging data at a doctor's office. Reading big image, writing big images. What happens if I take a number of those and put them on VMs and put them on the same data store and they're all working? All of a sudden that sequential read and sequential writes gets jumbled together, and it looks like a bunch of more random reads and more random writes. So it can make it tough. That's why it's often, I say, an art than a science, because if I have a bunch of servers I haven't virtualized yet and I take my performance data, I've got to kind of guess how they're going to do when they all start landing on the same disks. So again, you guess, I guess you say you kind of analyze it, and then you correct it if it's not right. What about storage interconnect? So I just hit on iSCSI and NFS a second ago, so let's talk about it. I don't care. VMware doesn't care. For this exam, we really don't care. What we care about are some of the particular nuances of each one. How do you configure FC? How do you configure iSCSI? How do you configure NFS? From a pure performance standpoint, they are all very capable, especially now with 16 gig FC, 10 gig, 40 gig iSCSI and NFS. That's not, the interconnect isn't the issue. Even 1 gig iSCSI and NFS can throw a lot of 4K or 8K IOPS across it. So it's rarely the problem. It's really up to you. There's a tons of pros and cons that we won't get into here, but it does not really matter. Most people greatly overestimate needed throughput. I believe this is true. I talk to customers all the time that think I'm crazy when I would recommend a 1 gig multiple 1 gig NFS or iSCSI connections. But what they forget is, more often than not, probably about 95% of the time, is that storage cares more about IOPS than throughput. There's a few kind of corner cases where throughput actually matters, but often it's all about the IOPS. What can those back-end disks do? not how much data I can throw across that cable at one time. NFS and iSCSI can use some CPU overhead, so this is one of the things that I'm going to kind of hit on for the exam. Honestly, I rarely see VMware environments that are CPU constrained. We almost always hit memory first. And with modern processors, with modern NICs, and with offload capabilities and iSCSI tow cards, there's not much of a CPU hit. I mean, these days, when you do Intel, basic CPUs with 6 cores each, 2 of them as often a minimum, or 8 cores or 10 cores, it's just not an issue. But for the exam, kind of understand that they can use overhead, whereas something maybe like a fiber channel card isn't going to have as much. If you need more, there are more options, right? There's 8 gig and 16 gig fiber channel. There's 10 gig NFS and iSCSI. There's 40 gig Ethernet right around the corner for a lot of people, so those are options. 10 gig fiber channel over Ethernet. And if you want to do iSCSI and you need more, you can do multipath to iSCSI. Can't do multipath NFS yet, but you can do multipath iSCSI and start bundling connections together. So if you do need more, there are some simple options for that. Now let's talk about some of the different pieces and parts. And I'm going to kind of put a little disclaimer. Sometimes you will see these courses or these lessons kind of jump around a little bit. This is one of the first times this has happened. This is one thing about this exam, is it's a lot of knowledge, and it's not a simple narrative as you walk through it like a VCP course would be, where we talk about installation, configuration, spinning up VMs. So there's a lot of times we'll hit different things as we go through. So excuse the sudden jumps and cuts at times, and this is one of the first ones. SCSI reservations. So at times, an entire VMFS volume will be locked by a single host. It's called a SCSI reservation, and really it's done so that no other hosts update the volume anytime there's some very specific operations done. And they don't last long. They're very quick, but they do lock the entire volume, so everything else has to wait. This occurs when you perform an action that causes a metadata update, creating, deleting, or changing the size of a VMDK file, increasing the size of the VMFS volume, snapshot creation, or deletion. Some of these things are getting better. We will talk about VAAI offloads to the arrays in a later lesson. And those will move some of this over to the array so we don't have to do SCSI reservations as often. But you will sometimes run into issues if you're doing heavy snapshot creation or deletion, or a lot of VMFS updates. And it used to be the reason that we would recommend you not put a lot of VMs on a data store. In fact, when I started at Vero, I think we said about 15 was what we were comfortable with as a maximum. Now, using these offloads, I don't care if you do 100, but we used to run into problems with SCSI reservations and LUN locking. It would issue a SCSI reservation, the LUN or the volume on the array would stop processing from others, hosts, do the change, and then release. Very quick, but if you do a lot of them, they start to add up. And I just said VAI can help minimize these, but it does require array support. The nice thing is, these days pretty much any reasonable array supports it. I'm sitting here looking at my Synology NAS, and these are kind of small office, home office type boxes, kind of moving in the upper end of small office. And the ones I have sitting here support VAI for iSCSI. They don't do it for NFS yet, but they do it for iSCSI. So you're seeing that be pretty prolific. Just make sure your array supports it. You don't need to update the software, the operating system on the array. Next is raw device mapping. So RDMs, as we call them, are something that I'm starting to see, I guess I would say, go away. They used to be used a lot more prominently. And raw device mappings are basically, I've got an iSCSI LUN or a fiber channel LUN. Basically, a fiber channel LUN or iSCSI LUN is a volume carved up and presented to the host. Normally, you would present them to your vSphere host and have vSphere, format them as VMFS. And then you would put VMs on them. But with an RDM, you can actually take that and then pass it up to a VM directly so it has access and sees that raw device. That's why it's called a raw device mapping. There aren't a whole lot of reasons to do this anymore. They can be larger than 2 terabyte on VMFS 5 in physical mode, and we'll talk about the modes in a second. They also allow direct SAN access for management tools. Sometimes we will run SAN monitoring tools, things like that, that needs direct access to a LUN to pass communications to an array over fiber channel interface. And so we'll have to do a small RDM for that. Also, sometimes you'll see it used in Microsoft clustering and things like that. But, for the most part, we don't see them used anymore. It uses a mapping file on a VMFS volume that acts as a proxy to raw storage. And this file allows some added functionality. Basically, what it does is there is a LUN that gets passed to the VM. Then you have a mapping file on another VMFS volume, so you have to have a VMFS volume, obviously. And it lets you do some things like, depending on the mode of the RDM, you could do some things like snapshots, other stuff like that. I mean, that's the main one is snapshots. And let it do things even though it's a raw mapping. Not something I recommend you use often, unless you have to. Several reasons, again, for use. Microsoft clustering being one, requires physical mode RDMs on occasion. SAN management tools, large single volumes over 2 terabyte. We can do that now, but a lot of people get confused. So I can give you a 64 terabyte VMFS volume, but the largest VMDK is still 2 terabyte. What if I have a server, Windows machine, a file server, and I need a 10 terabyte volume? You got two options. One, create 5 2 terabyte VMDKs, and then use, say, Windows disk tools to stripe across them and make a 10 terabyte volume. I've seen that done. Or create a 10 terabyte RDM and pass it up to the host. So that's one of the use cases, is large volumes. Or connecting legacy block storage to a specific VM. What I mean by that is I have had customers with physical servers. I SCSI'd over to a volume, maybe even a terabyte, formatted with NTFS. We virtualized that server, and then we would just pass that formatted volume direct to the VM as an RDM. So that's an option as well. That way they could just reattach to it and they wouldn't have to reformat it. Normally I would say convert that to a VMDK, but it does allow you to connect legacy block storage to a new VM. There are sometimes use cases for that. It is not needed for higher performance, so that's an older myth. It used to be I would run into this all the time. Hey, do you guys use RDMs? Yeah, we've got a bunch of RDMs. Why? Performance. We couldn't get to performance we needed with VMFS. So normally that's not true. Normally there was another issue. And especially these days. The real world performance difference between VMDKs and RDMs, VMware is going to tell you none. I would tell you probably 1 to 2%. And I always tell people, if you're within 1 to 2% of your 100% maximum on storage, you've got bigger problems than us trying to figure out if you need to use RDMs or not. You don't need to be that close anyway. So performance is not a reason. The reasons to use RDMs are those 4 reasons above at the top of the slide. So there are 2 types of RDMs. I kind of bumbled through this in the first part, but there are 2 of them. There's what we call physical mode RDMs, and those are the most quote-unquote direct. VM kernel passes all SCSI commands to the underlying device except for one, which is the report LUNs command. Is that important to know? Probably not, but it's good to know for the exam. They can be up to 64 terabyte in size. Again, I can present you to your VMware host a 64 terabyte VMFS volume, but on a VM, I can't make a Windows 2008 VM with a larger than 2 terabyte VMDK. If you need a single volume larger than that, you can do up to 64 terabyte and pass it through. Again, required for SAN management tools. Limitations include no snapshots or file locking. So I mentioned mapping file and snapshots a minute ago. That's not acceptable on physical mode. Physical mode is as direct as you can get, except for the report command. But you don't get any of the other cool VMware functions. You don't get to do snapshots and stuff like that. So keep that in mind. It's one reason that I just don't see a lot of these things used. Then you can't do snapshots. You can't do easy backups, kind of VMDK level backups. You can't do any of that stuff. So it's just not a great idea. Then you have virtual mode RDMs. They're a little bit more feature rich. They appear to a VM as a VMDK. They can do snapshots, but they can only be 2 terabyte minus 512 bytes in size. So they're very much like a VMDK. They are just, passed through directly to the VM, unlike a normal VMDK. So which do I use? Well, it depends on what you're doing. Clustering, large volumes, or SAN management, use physical. Else, use virtual. Why would I use virtual? I don't really have a great reason for that. there's not a lot of good reasons to use a virtual mode RDM. Usually, if you have the reason, use physical. If you don't need physical, you don't need virtual mode RDMs. But it is an option out there. Understand how they're both different. We'll show you in the lab how you create and configure these here in just a bit. But again, most of the time, if you need one, it's going to be physical. Requirements for RDMs: block storage only. Can't do RDMs against an NFS volume because it doesn't have a concept of a LUN. Can't be created on local storage. So if you've got a vSphere box with a local disk in it and you want to play around with RDMs, too bad. What you could do is get something like FreeNAS as a VM that will present things out as iSCSI and then loop it back. But other than that, you can't access direct local storage. For RDMs larger than 2 terabyte, you must be on VMFS5. And it's just like your data stores. To go above 2 terabyte on data store, you got to be VMFS5. Same with your RDMs. So let's compare RDMs and VMFS. VMFS should be your standard. Only use RDMs for those special exceptions. And in almost all cases, VMFS performs as well or better than an RDM. So it's a common misconception about performance, but really, if 1 or 2% is a big deal, and it shouldn't be, I think the benefits of VMFS far outweigh RDM, except in those very specific cases. Not to mention, like I just said, VMFS is easier to manage, more flexible, things like that. And it's just really more about this mobility and this encapsulation and abstraction of virtualization. I push people to get away from RDMs, again, unless you specifically have a need for really large volumes in a guest or something like that. And in those cases, just pick and choose wisely. So now let's jump to a lab. We're going to do a quick lab where we create an RDM. Pretty simple, but I want to show you the process in case you've never done it, or if you don't have access to a block-based storage array that you can do it. So with that, let's jump to the lab. So here we are. What I've got is pretty simple. This is a Windows XP system. I've already loaded up the disk management tool, and we can see there's a C drive, and that's it. So what we'll do is we'll go to VM. We'll go to Edit Settings, and I'm going to add a disk. There we go. Hard disk. And it gives me some options. Probably some you've seen before. So do I want to create a new virtual disk, use an existing, or an RDM? I'm going to choose RDM. And what I'm doing is I've got my Synology NAS presenting some iSCSI block-based LUNs to my systems. So we'll say Next. And it says which LUN do you want to use. I'll just use that one. And specify the data store. Remember, we have a LUN mapping file. So I'm just going to put that on data store 4. That's fine. And it says, do you want to do this as physical mode or virtual? Again, remember, physical is basically as close as you can get to actually passing that LUN to the VM. Whereas virtual gives you some extra capabilities like VMware snapshots. It kind of depends. There's a couple of use cases for clustering for physical, else you probably want to do virtual. I'll just click virtual. The process is the same. And then virtual device node, it'll say, which SCSI device do you want to show. And just like normal for disk, you can set the mode either independent, persistent, non-persistent. You don't see this in physical because, again, you don't have access to snapshots. So that's the difference there. Say Next. It'll say, do you want me to add this? And I say, absolutely. And we'll say OK. We'll see the task kick off. We'll come over here. May need to do a scan. Click, right click. Rescan, and now we see the 500 gig volume. So again, it's really simple. There's not a lot to it, but again, the use cases are kind of particular. Don't get caught up in doing these a lot, but it's not hard to do if you need it. So that's it for the lab. Jump back to the presentation, and that's it for this lesson. So that kind of walks you through a lot of this. We're going to continue on with some storage management as we move along the path. So I look forward to seeing you on the next lesson.